Okay, now we're getting into that blurred area where we're dealing with sometimes circular motion and sometimes straight line motion, and we have to be able to resolve between the two. Because technically, the motion of an object going in a circle, the speed is the same as the velocity, but it differs in the fact that it is changing in direction. But if you take a look at the speed at every particular point, it's identical. So if we are able to state that the straight line velocity at any particular point, like the tangent, is to be the same as the straight line point tangent at any other part of the circle. But it's involving circular motion while all that's going on. So there's going to be three formulas in this particular section that you're going to need to work with. The what we call the centripetal acceleration. The centripetal means being pulled towards the center. The reason why the ball doesn't fly out of your hand going off of the tangent is because the string is pulling you back in as you're pulling that thing around. The formula for that is v squared over r, and I'm going to derive these things for you so you see what's going to happen to this. It's also measured, this is in a linear fashion, this is in a circular or angular fashion here. And then centripetal force, it's the force pulling the object towards the center as it's trying to get away from the center, is mv squared over r. So these three formulas are going to be important in this section. So let's talk about how we got that. Now, this is an example of a circular motion with some object traveling in a circle here, and if you were to release it, it would go off in these tangents right here, V1, V2, V3, and so on, all the way around, with a particular angle of theta here, and this is the radius right here, and here. And these arrows here are showing the centripetal force, or in this case, centripetal acceleration at each of those points as well. Now, like I said, all three of these values are equal. And we know that the acceleration, the linear acceleration, is equal to the linear velocity over delta t. Now these mean vectors here, which is not, this is not going to turn to a vector problem, so don't freak out there. But one of the things that physicists use, and particularly since we're dealing with calculus, and every once in a while you see this crop up, they use the letter S for distance. Not sure why, but it's there, and we got to be dealing with it. And as you know, distance is velocity times time. So if you take a look at the velocity at each of these points, the distance traveled is the velocity times the time it took to go from point A to point B and point B to point C. Okay? Now, here's where calculus people will have a little bit of experience in what happens next. If we were to say that this distance right here, this curved distance right here is S, and we also know that as these get closer and closer and closer together, that ratio of delta V and the velocity is approaching zero, as is the S, the distance here approaches zero in relation to the radius. So this is where this equation is coming from. V2 minus V1, these two velocities here, divided by the overall velocity, is approximately equal to S over R. And so we can see how this relates here. When we write down V2 minus V1 over V, we can rewrite that as delta V over V. Now delta V over V is going to equal to the velocity times the change of time over the radius. Now, that is basically saying that this distance right here can be calculated from this, which we established from this. So that's where that's coming from. We're just plugging that value in right now, just so we can deal with some algebraic expression here for limits. Now this is happening as the change in time approaches zero. So the closer these get, the more this turns out to be not approximately equal to, but equal. And that's why we say as delta t approaches 0, this changes from approximately equal to equal. Now we can do some mathematical manipulation of these two now equations. And so we've got this right here. So I'm going to multiply this v here on both sides. That cancels out there, leaves delta v. And that gives me v squared times delta a, delta t rather, over r. Then, the next thing I'm going to do is I'm going to take that delta t that I have here and divide by that. And that gives me delta v over delta t, which is acceleration. And what we have left over then is v squared over r. So we get that equation we had for centripetal acceleration as being v squared over r. That's where that comes from. It's just a little bit of calculus. And many of you who are going to be taking physics in college, you're going to be taking a calculus version, particularly if you're getting into engineering. Okay? So have fun with that. So the next two equations I had after that is where if you know that the centripetal acceleration is v squared over r, and we know from previous section that we can change angular velocity, linear velocity, or vice versa using this formula right here. Remember, omega is the angular velocity, but we have to multiply that by radius to get that in terms of angular or straight line velocity. Then, if we plug that in right here, we get this equation right here. Parentheses r omega squared, or r times angular velocity squared over r. Well, that gives us r squared here, r here. That cancels out, leaves r. We have omega squared here. So the angular acceleration we can get by taking r times omega squared. Now, we could have, well, we'll get back to that. So I had a thought in my mind, and I decided not to share it because I don't want to confuse it. So understand that's what's going on with that. Now, since we know that force is equal to mass times acceleration, then it stands to reason that centripetal force equals mass times centripetal acceleration. And if that's the case, then that means then that we can replace acceleration, centripetal acceleration, with v squared over r. Put that right there. And now we have centripetal force to be measured as mv squared over r. And there's your three equations that we're looking at. So let's take a look at a couple problems in the book. We'll open up page 261. And let's take a look at problem number 31. In problem 31, if you take a look at it, you see that you're given the acceleration, the centripetal acceleration of the 1.2 meters per second squared. And the question is, what is the velocity of that object at that point if it would go off in a tangential direction? Okay, so since we know that A now equals v squared over r, so we have a radius of 1.5 and an acceleration of 1.2. So this becomes 1.2 meters per second squared equals v squared over r. And r here is 1.5 meters. So now you can multiply both sides by 1.5 meters to get v squared by itself. So we do that and we get v squared is equal to 1.8 meters squared. Because meters times meters squared over seconds squared, which is right there with meters. Take the square root of both sides. That means this becomes meters per second. And if we take a look at the calculator for the square root of 1.8, we get 1.24. And the label, like I said, is meters per second. Okay? Alright. Second problem we're going to look at is number 33 on the same page. We have a centrifugal force of 4 G's. Now, G is a way of describing gravitational acceleration, like we use the equation for finding forces of, well, we haven't gotten that yet, but when we're using weight, force in terms of weight, G is what we use. So when they say G forces, they really mean that this is 4 times 9.80 meters per second squared. And when they do engineering for amusement park rides, G forces are very important. They don't want people vomiting all over the place, so they have to make sure that the G forces stay within a certain bounds of keeping stuff inside your stomach. So when we do that, we get 39.2 meters per second squared. Now, again, we're using the formula B or BC is equal to B squared over R. So that means we're going to have 39.2 meters per second squared equals B squared, that's 50 meters per second squared over, velocity is not meters per second squared, that's just meters per second. So we fix that, and that's squared, divided by R. And again, in algebra, when you have a variable in the denominator, you simply flip these two, this equation. So this becomes R is equal to 50 meters per second quantity squared over 39.2 meters per second squared. The second squared we cancel out, and you got 2 meters squared here, meters here, so we cancel out. We need 1 meter on top, which is what you want for your radius. And when the smoke clears, this turns out to be 63.8 meters for the radius. That's how you use those problems. So, your homework assignment, 30 through 36, even on page 261. Have fun!